Hello everyone, and welcome to my presentation on selective in-context data augmentation for intent detection using Pointwise V information. I'm Yen-Ting Lin from National Taiwan University, and I have the pleasure of working with my intern mentors and manager in Amazon Alexa AI on this research. The availability of high-quality training data is crucial for the success of any machine learning models. However, in real-world applications, we often face data scarcity and limitation in collecting diverse and representative samples. This results in models that are biased and lack generalizability. To address this issue, we propose exploiting the potential of large language models, LLMs, for generating synthetic examples. LLMs have shown remarkable progress in generating text that is almost indistinguishable from human written text. And we can leverage this capability to efficiently generate diverse and high quality synthetic training sets. However, there are challenges in ensuring the relevance and the quality of the generated examples. LLMs can sometimes hallucinate and diverge from prompts, producing low quality examples. Therefore, ensuring the relevance and quality of the generated example is critical for downstream model performance. To address this issue, we have developed a method to filter our irrelevant or unhelpful example from LLM generated data. To further enhance the quality and the diversity of our synthetic data, we propose AI-AI synergy. This involves using LLMs to generate initial examples, where are then filtered using downstream baseline model. The filter example are then used to train a new downstream model. This data augmentation framework combines the strengths of both AI model, resulting in more accurate and diverse synthetic data. This approach not only improves the quality of the data, but also reduces the time and cost required for manual data labeling. Our task is intent detection, which is a vital component of conversational system. In order to understand the user's current goal, the system must leverage its intent detector to classify the user's utterance into one of several predefined intents. The accuracy and the efficiency of the intent detection directly impact the overall performance and user experience of a conversational system. Therefore, it is crucial to have a high quality training data to train and improve the intent detector. We propose ICDA, in-context data augmentation. The ICDA framework involves four main steps: exemplar collection, overgeneration, PVI filtering, and classifier training. Let's take a closer look at the first two steps of our ICDA framework: exemplar collection and overgeneration. To collect exemplar, we start with a few shot set that consists of a small number of examples for each intent. For example, consider the following 10 sentences belonging to the same category as refund not showing up. We can use these examples as exemplar for our refund intent. Then we use an LLM to overgenerate synthetic examples based on these exemplars. The generated sentence belongs to the same category as the exemplar. Moving on to the third step of our ICDA framework, PVI filtering. PVI, Pointwise V information, is a measure proposed by Cowan et al. It measures the degree of usable information in individual instances. Intuitively, high PVI instances are easier for the model to predict correctly, while low PVI instances are harder and may not be useful for training. And negative PVI indicates that the model is better off predicting the majority class than considering the input instance. which may happen due to mislabeling. By filtering out low PVI instance, we ensure that only the most relevant and useful examples are included in the training data, which can significantly improve the accuracy and efficiency of the downstream model. To determine the PVI threshold for filtering, we calculate the average PVI of the validation set for each intent. Any generated example with a PVI score below the threshold is filtered out from the augmented dataset. For example, consider the refund not showing up intent with 4 examples. 2 of them have high PVI values, indicating they are useful for training, while the other 2 have low PVI values and may not be helpful. The final step of our framework is to train our intent classifier using the original dataset and the augmented dataset. We use a BERT-based classifier to train on the combined dataset. For our experiment, we evaluate our framework on 3 challenging intent detection datasets: Clink, Banking, and HWU. These datasets consist of various intents, and we evaluate our approach under different settings, including 4-shot, 10-shot per intent, and 5-shot per intent. We compare our approach with the previous state-of-the-art models and a baseline model that use only the original data or the unfiltered augmented data. Our experimental results show that our ICDA framework achieves state-of-the-art results on all 3 datasets under few-shot settings. This demonstrating the effectiveness of our approach in generating high-quality and diverse syntactic data. For more detailed results on our experiment, please refer to our paper. Our experimental results also show that PVI filtering is necessary for achieving the best performance. We compare different filtering strategies and report the result in the table. Our results show that models trained with PVI filtering outperform the model trained without filtering, indicating the importance of filtering out low quality or irrelevant examples. Furthermore, our results show that low PVI syntactic examples are generally not helpful and may even harm the downstream model's performance. Models trained with high PVI example outperform models trained with low PVI example. This emphasizes the importance of PVI filtering. Our results also show that the setting of a PVI threshold for each intent class is important. Model trained with per intent PVI threshold outperform model trained with a global PVI threshold across all intents. This indicates that each intent class has its own characteristics and requires different levels of filtering. Finally, we also evaluate the fluency and diversity of our syntactic examples. We use 3 metrics, distinct 1, distinct 2, self-blue to measure diversity, and perplexity to measure fluency. Our results show that ICDA produce syntactic examples that are both fluent and diverse. These examples are more diverse and have a similar level of fluency compared to the original few-shot sets, indicating that our framework can generate high quality and diverse examples. In summary, we have introduced a novel approach for data augmentation in intent detection using large language model generation and pointwise V information filtering. Our approach ICDA achieves state-of-the-art few-shot performance on intent detection datasets. ICDA's success can be attributed to producing diverse and fluent alternatives while discarding mislabeled syntactic examples, resulting in improved accuracy. Our approach not only improves the accuracy of the intent detection, but also reduce the cost and time required for manual data collection and labeling, making it a valuable tool for real-world application. Thank you for your attention. If you have any questions or comments, please feel free to email me at ytl@ieee.org. Thank you again and have a nice day.